Let's talk about acceleration. So far what we've learned is that with velocities you have to calculate the positions of things first and then you can calculate velocities. Well, to calculate accelerations you have to get the position, then the velocity, and then go for the acceleration. So that's a general theme of this strategy. Let's read through this slide. As the bicycle accelerates a point on top of the wheel, we'll have acceleration due to the acceleration from the axle. In other words, the bike itself is probably accelerating forward or backward. The tangential acceleration of the wheel from the angular acceleration, so in other words, the wheel's speeding up, so there will be a tangential acceleration. And normal acceleration due to the angular velocity. So because the wheel is rotating, that point, if you imagine standing on the axle and looking at the wheel rotate, that point would have a normal acceleration pointed towards the center of the wheel. So all of those accelerations together would have to be considered in order to understand the total acceleration of that particular point at the top of the wheel. So hopefully this gives you the idea that acceleration is a little more complicated than velocity analysis. That is the case, but it's not as complicated as you might think. As a matter of fact, we always break down the acceleration into two parts, and I'll show you what I mean. Just like we've done so far, we're going to look at acceleration just as a vector and talk about it as a vector that's a property of one point equals the vector that's a property of another point, which hopefully we already know, plus a relative vector between the two. And in particular, we're talking about acceleration. So just like with velocity, this breaks down really nicely where we say the acceleration of point B is equal, it's just the same as the acceleration of point A, so that's, again, this term after the equal sign matches the potato body after the equal sign, plus a relative acceleration, which you can think of due to motion about a fixed point A. So we're looking at the motion of B about A. And in particular, we're looking at acceleration. Now what's interesting about this is if the body is only rotating about A, then point B is only going to have two components of acceleration with respect to A. In other words, point B can still only move on a circle about A. Therefore, point B can only have a normal acceleration pointed towards point A. It can't point the other way, but pointed towards point A that is dependent on the angular speed of the body. You can think of it as the tangential velocity in that radius there from A to B, plus a tangential acceleration which is due to the angular acceleration of the body. What's so nice about this, see, is that the acceleration of point B with respect to A, that relative acceleration term, will always break down into two pieces. One piece will be a normal acceleration pointed back to the reference point, which is point A, and an acceleration that is a tangential acceleration that is directly related to the angular acceleration of the body. So this always breaks down really nicely. That second term, acceleration of B with respect to A, is always the sum of a normal and tangential acceleration. And that's what you're looking at in the vector triangle over there. This says the acceleration of B is equal to the acceleration of A plus the relative acceleration of B with respect to A. And oh, by the way, those dotted lines are the vector sum that make up that relative acceleration. And they're always a normal and tangential piece. And the reason for doing this is because that normal piece will always be related to the angular speed of the body, and the tangential piece will always be related to the angular acceleration of the body. So that makes it break down really nicely. As a matter of fact, the tangential vector itself is just the angular acceleration of the vector, you see that alpha k, crossed with the position vector from A to B. So imagine, well, you can see the vector there on the figure, it's in black. It's the vector that points from A to B. In scalar form, that's just the distance r between A and B multiplied by alpha, the angular acceleration of the body. So looking at that equation, next to last row on the slide, they've just written the equation again in scalar form. And then finally the last row, the normal piece of that acceleration is just the square of the angular velocity times the negative of the vector from A to B. And the reason it's the negative is because the normal acceleration always points from B back to the reference point A, and so that's in the negative normal direction. I'm sorry, pardon me, that's in the negative direction to the vector RB with respect to A. Sorry, I didn't mean normal. And then finally, in scalar form, we can just write that as r omega squared. Now you notice that the negative sign has gone away. It's because we're just dealing with magnitudes, and we understand that the direction of that normal acceleration has to point towards the center of rotation, A. That's our current focus, or our reference is A. And so just like if point B is moving with respect to A, it can only rotate about A. And so the path that point B would be on would be a circle fixed, well, whose center is at A, and therefore the normal direction is from B to A. So given the acceleration of a particular point and a velocity at that point, we'd like to determine the linear acceleration of another point on the same body and the angular acceleration of the body. So how on earth would you do that? Well, the first key is to realize we're always going to write a relative acceleration equation. So, pardon me, if you look at the first image on the left, you'll notice that we've got plane motion of this mechanism. The acceleration of A is off to the right. The acceleration of B at this point, we're not sure if it's up or down unless you have some intuition. And even then, you might be wrong. Be careful about using intuition here, because it's possible that B could be accelerating up or down. But we're always going to write the acceleration of point B in terms of the acceleration of point A, which is known, plus the relative acceleration of B with respect to A. But what's nice about that, like I said, is that that relative acceleration of B with respect to A is always going to be written as a normal piece and a tangential piece, and you see that that's what's been done in the next row. Now we have to be careful here. Notice the last figure doesn't make it clear which direction the tangential acceleration or the relative tangential acceleration is pointed. It could be pointed up and to the right or down and to the left. And you'll see why it may be one or the other in a minute. It depends completely on two things. And you'll see that in just a second. So let's take the case where the acceleration of point A is to the right. If A is accelerating to the right, well then the normal acceleration always points, now this is the relative normal acceleration, right? Because it's the acceleration of B with respect to A in the normal direction. That vector has to always point along a line from the point we're asking about, B, back to the reference, which is A. Because again, remember that we're thinking of this as simply a translation plus a rotation. But of course we're talking about acceleration now. So the direction of the normal vector has to be from point B to point A. So if we take the acceleration of point A and add to it that normal piece, we're going to have to add the tangential piece, and we'll end up with the acceleration of point B. That's what the equation says. So you notice that we've got the acceleration of A, that's that horizontal line in this vector sum, this graphical vector sum. The normal acceleration of B with respect to A, the relative normal acceleration, is down and to the right for sure, because it has to point from B to A. And so if the tangential acceleration were up and to the right, there's no way we could end up with a vertical acceleration of B. And because of constraints on the mechanism, we know that the acceleration of B has to either be up or down. It can't have a sideways component. Why not? Well, if the acceleration of point B had a horizontal component, that means that the point would have to gain a horizontal velocity. And to gain a horizontal velocity means that the mechanism would have to start moving such that B is moving to the right or to the left, and so it'd have to come out of the track. That's not okay. B has to only have an acceleration that's vertical. And so it's not possible, if the acceleration of A is to the right, it's not possible for B to accelerate upward, because the tangential acceleration, the relative tangential acceleration, has to point down in order to give rise to a vertical acceleration for point B. But what about the other case? What if instead A is accelerating to the left? Well, then it'll depend on a few things. So let's pretend that the normal acceleration is fairly low. How would we do that? Well, if the angular speed of the body is fairly low, then the normal acceleration will be fairly low. Let's pretend further that the angular acceleration of the body is fairly high. Therefore, the tangential acceleration, the relative tangential acceleration, AB with respect to A sub t, would be fairly high. Now, again, the normal relative acceleration, the acceleration of b with respect to a in the normal direction, that's going to be fairly short because the angular velocity is fairly small, but it still has to point from b to a. So we'll just draw a short vector. You see it there in the left of figure b. And then the tangential piece would have to go up and to the right in order to give us an acceleration of point B that is vertical. So in order to complete this, it's not a triangle anymore, it's a force polygon really is what it's called. And, pardon me, an acceleration polygon, where I'm used to thinking of force polygons. You can do this with forces as well, which is kind of interesting. That's what you do in statics, you just sum forces. Technically, it's what we do in dynamics too. It's just one of the forces is a dynamic force. Anyway, moving on. This is an acceleration polygon. If the relative normal acceleration is fairly small and the relative tangential acceleration is fairly large, then we'll end up with an acceleration of b that's actually upward. That is a possibility. Let's take the next case where we have a decent angular speed and a decent angular acceleration and an acceleration of a to the left. Well, in that case, the normal acceleration still, or the relative normal acceleration, still will point from b to a, so it's down and to the right like it has been all this time. And to complete the acceleration polygon, we'll have another vector added, the tangential relative normal, or tangential relative normal acceleration from the tip of the normal piece back to construct vector a sub b, the acceleration of point b. And you can see that the acceleration of b would end up being downward in this case. Taking it one step further, what if the angular velocity of the body is very high, but the angular acceleration is very low? Well, in that case, that relative normal vector might actually cross over point b and require that the tangential piece be down and to the left in order to, again, construct an acceleration for b that's vertical. So these are the three cases that are possible, and just depending on the angular speed and angular acceleration, they're going to vary. Now, really, what does it depend on? Remember, we're trying to solve for the angular acceleration, so how would you do this ahead of time? Well, understand that tangential piece, the acceleration of b with respect to a, that tangential piece is computed, in other words, it's drawn in order to make the acceleration vector for b vertical. So really, in essence, what we're doing by drawing these acceleration polygons is solving for that tangential piece, which is then directly related to the angular acceleration. So the sense of the acceleration the tangential piece. Sorry, I'm trying to reconcile what's written here with what I'm thinking, and I'm getting tired. So the vector, let's just read it and talk through it. The vector result depends on the sense of the acceleration of a, whether it's to the right or the left, and the relative magnitudes of the acceleration of a and the normal relative acceleration. And that does make sense because that's basically what we've said so far, right? Because that tangential piece, the acceleration of b with respect to a, that tangential piece, has to finish off this acceleration polygon in such a way that we end up with a vertical line for the acceleration of point b. So notice that we also have to know the angular speed of the body in order to deal with this. Otherwise, we can't solve the problem. And this, as I said, is a general principle. You have to know the position solution first, then the velocity solution, which includes the angular velocity solutions, before you can come up with the acceleration solution. All right, so how do we solve this? Well, basically what we're going to do is just write this relative acceleration equation in terms of the two components. So we're going to have an x component, and if you think about the acceleration of point B can't have an x component, so that's 0 on the left-hand side, plus whatever the acceleration of A is in the x direction, plus what is this L omega squared sine of theta? Well, that is the normal piece. Remember that the normal acceleration can be written as v squared, the tangential velocity, over the radius of curvature, which is the distance between A and B in this case, or it can be written as that length multiplied by the angular speed squared. And so that's where this L omega squared comes from. Well, where does the sine of theta come from? Well, notice that the normal vector has a component in the x direction and the y direction. So we're just taking the x component of it by taking sine of theta. And you might say, well, I thought you use cosine to take the x component. Well, you've got to look at how theta is defined. And if you look at how theta is defined in this problem, we have to use the sine piece, not the cosine piece, in order to get the horizontal component of the relative acceleration of b with respect to a. That's just the normal part. And that's what's drawn here in the third figure over, or the last mechanism figure, that's moving from, or pointing from b to a. And then finally we have the tangential piece, that's this last term, minus L alpha cosine theta. And what is this? Well, this is just the horizontal component of the tangential, the relative tangential acceleration vector. Almost said velocity there. The y component of the relative acceleration equation would be the acceleration of point B, which is an unknown. So we're writing negative acceleration of point B. Why is it negative? Well, you can see from the polygon that was drawn that it's in the negative direction. Equals the acceleration of A. A is still in there, it's just 0, and we didn't write it. And then minus, you notice that the normal component, the acceleration of b with respect to a, the normal piece, has a negative vertical component. We're talking about a y-axis now, so that's why there's a negative sign. Still, the magnitude is L omega squared, and to get the vertical piece, we have to use the cosine of the angle theta. And then finally, the last term here, negative L alpha sine of theta, is just the vertical piece of the tangential vector. So then you solve for the acceleration of b and the angular acceleration, and you're done. That's the general strategy here. Now, sometimes you can just write it down directly, and it's simpler that way. So, for example, we can write that the position of point A is equal to L sine theta, and the position of point B is L cosine theta. Then, if we simply differentiate the left and right-hand sides of both equations, we get that the velocity of A is just simply the rate of change of the position of point A. And so if the position of point A is L sine theta, then just take the derivative of it. Now, L's not changing. The sine theta is the only thing that's changing. But you have to use the chain rule here. If you don't remember it, you could mess it up pretty easily. So what you do is you take the derivative of sine of theta, because the L is just going to be a constant, and you get cosine of theta multiplied by the derivative of the inner function. Remember that theta is something that is changing with respect to time as well. So you have to take d theta dt, which is just theta dot. And that's why it's included as a multiplication factor. They just put it at the beginning so you didn't think that you were trying to take the cosine of theta times theta dot. And so theta dot is better known as omega, the angular speed of the body. So the velocity of point A is just L omega cosine theta. Looking at the y component equation, the velocity of point B is just the rate of change of the position of point B in the y direction. And so taking the derivative of yb equals L cosine theta, we'd have the same thing, right? L's not changing. We just have the derivative of cosine, which is negative sine, times the derivative of the inner function. Again, that theta becomes doesn't become, but the derivative of theta, the rate of change of the angle with respect to time, is just theta dot. And so you can write it again. You have to be careful when you do this because sometimes the signs don't come out right, the SIGNs. This makes sense because if A is moving to the right, then B would be moving down. And so the velocity of A would be positive to the right, velocity of B would be against the coordinate, which would be down. So this makes sense. And then to get the accelerations, just take the derivative again. Now, this gets into a little bit more difficulty. You notice that L is just a multiplier, so it could come out technically. But when you take the derivative of theta dot cosine theta, you have to hold the theta dot constant, first of all, and take the derivative of cosine theta. Well, that's minus sine. Well, then why do they have theta dot squared here? Well, don't forget that inside of that sine of theta, that theta still changes. So using the chain rule again, you get another theta dot out, and they just combine them together. So that's where the negative L theta dot squared sine theta comes from. And then to get the other piece, again, the L is just a constant. But what they're doing here is they're taking the derivative of theta dot. So they get theta double dot, the second derivative, multiplied by cosine theta. They're holding that second term constant in L theta dot cosine theta. And so theta dot is better known as omega, so they just make that substitution in the last line on the left-hand side. And theta double dot is better known as alpha, the angular acceleration of the body. And they do the same thing, differentiating y dot b again to come up with the expression for the acceleration of point B. All right, concept question. You have made it to the kickball championship game. As you try to kick home the winning run, your mind naturally drifts towards dynamics. Yeah, sure. Which of your following thoughts is true and causes you to shank the ball horribly straight to the pitcher? Energy will not be conserved when I kick the ball. Now, as a thermodynamics teacher, I have a problem with this statement because what they really mean is that the mechanical energy of the ball will not be conserved. And that should make sense to you in terms of dynamics, because when you have an impact, in this case between your foot and the ball, you know that your foot's going to be in the air hitting the ball. The momentum will be conserved. Well, not exactly. There's also some angular momentum of your leg to be concerned with, but let's neglect that for now. Just what we learned back in impact and impulse and all of those things. The momentum would be conserved, but the energy would not be, right? There'd be some losses in your foot deflecting and the ball deflecting, and the fact that when they come back out to their normal shapes, that process is not lossless. Some of the energy in that kick would be transferred into the ball oscillating, or the ball, when it rebounds and comes back to its normal shape, the springiness turns some of the lossiness of that springy nature of the ball turns some of the energy into thermal energy. So when they say the energy is not conserved, what they really mean is the mechanical energy is not conserved. Let's consider point B. In general, the linear acceleration of my knee is equal to the linear acceleration of my foot. Well, no, that's not true, because your knee is a pivot point. And so the linear acceleration of the knee and the foot are easily different. See, throughout the kick, my foot will only have tangential acceleration. No, your foot's rotating about your knee again, and so there must be some normal, or at least relative normal acceleration. So C doesn't make sense. D, in general, the angular velocity of the upper leg, or the thigh section, will be the same as the angular velocity of the lower leg. No, that doesn't make sense. You've got a pivot point at your knee. And unless you've got a stiff knee, the angular velocity of your lower leg and your upper leg are going to be different. So the only answer possible is A, and that's the one they were driving us toward, but I had to clarify that what they really mean is that the mechanical energy is not conserved. There are some example problems. In fact, there are 3 that I want you to go through and see how this is applied. Again, I have my own that I want you to watch, but I think that going through both of these will, or all of these, will help you understand the concepts a little bit better. I'm just trying to get to the next slide so that you don't see the answer. Here we go. I do want to go through the group solving problem because I think I can explain some important concepts to you through these problems. Knowing that at the instant shown, bar AB has a constant angular velocity of 4 radians per second clockwise, determine the angular acceleration of bars BD and DE. Well, before you even tackle the concept question, understand you're going to have to calculate the angular speeds, or the angular velocities, of BD and DE as well before you can even think about the angular acceleration, but we'll get there. So which of the following is true? A, the direction of AD, the acceleration of point D, is up and to the right. Here they're trying to trick you. That's certainly the direction of the velocity of point D, but the acceleration would have to have a normal component, right? And so A is possible, but not very likely. In fact, actually A is not even possible, because D, if length DE is accelerating, then what they've drawn here only represents the tangential piece of acceleration. DE is certainly rotating, and therefore there must be a component that's normal, and so there's no way that A is correct. B, the angular acceleration of BD must also be constant. Angular acceleration of BD, how can we defeat that one? I'm not sure. Let's go to C and see if it makes sense. C, the direction of the linear acceleration of point B is to the right. Well, if AB is rotating at a constant angular speed, then that means B doesn't have any tangential acceleration, which would point up and down. And in fact, the normal acceleration of point B would have to be pointed towards A, so I think C is true. And see if we can figure out how to defeat B besides just process of elimination. We know it must be wrong because we know C is the right answer if only one of these is true. The angular acceleration of BD must be constant. Well, no, that doesn't make sense. That's position dependent. The angular acceleration is going to depend on... No, there's no way. Understand that what they're saying here is that the angular acceleration would be constant throughout the entire motion, and there's nothing to guarantee that we've learned so far. So, no, C is the only possibility. All right, I do want to go through this one with you. Again, the way you should go through this is by pausing the video and thinking about the questions, thinking about how you would solve this problem, and then following along to see if it made sense. Okay, so knowing that at the instant shown, bar AB has a constant angular velocity of 4 radians per second clockwise, determine the angular acceleration of bars BD and DE. That's what this is just the problem statement from the previous page. As I said, the first step will be to calculate the angular speeds, but that was done, if you remember, before in the group problem solving. So if that's already done, how do we determine the angular acceleration? Well, we're going to have to relate accelerations of points that we know to accelerations of points we don't know. For example, you know the acceleration of point A and point E is 0. That's simple. So you could relate the acceleration of point A to the acceleration of point B. As a matter of fact, point B, as I pointed out before, would only have a normal acceleration. And probably the best way to do this, since we know the angular velocity of what I would call the input, which is AB, probably the best way is to step through the mechanism from A to B, from B to D, and D to E, using some information, for example, that we know that D moves on a circle. Let's see what happens. So the first thing we're going to do is write the velocity of D in terms of the velocity of B. Well, that makes sense because we have to solve for the velocity. I guess they're going to go through this and do it. No, it says it was determined. I'm sorry, they're referring to what we did before. Okay, good. The angular accelerations are now determined by simultaneously solving the component equations for the relative acceleration equation. In other words, we're going to write angular accelerations in terms of points that we already know. So they're just noting that from previous solutions we found the angular velocities of BD and DE. And so we know that the angular acceleration of AB is 0. So we're going to analyze bar AB just like I figured. So the acceleration of point B is being written in terms of the acceleration of point A, which is 0, and the angular acceleration of point A, which is a tangential, the angular acceleration of body AB, and the tangential and normal components. So looking at this, what are these things? Well, you should begin to recognize alpha AB cross RBA as the tangential acceleration piece of point B. B has no tangential acceleration. It only has normal acceleration, and that's what that omega squared AB RB with respect to A is talking about. It's the normal acceleration. And all it's doing is pointing out that the vector R from A to B points to the left, but the normal acceleration of point B has to point to the right. So that's why that negative sign is there, along with the angular velocity of AB. And so all that's left for the linear acceleration of point B is the normal piece, which is negative omega of the body squared RBA. And so they just write this all out explicitly to come up with the angular acceleration, the normal acceleration of B, which is just to the right. It's in the I direction. We're using a normal x to the right, y up coordinate system. Analyze bar BD. So now that we know the acceleration of point B, let's step then to point D. So here we're writing the equation that is a relative acceleration equation for point D in terms of point B. And you'll notice that there's the acceleration of point B, the acceleration of D equals the acceleration of B, plus the tangential acceleration piece due to the body's motion, plus the normal acceleration piece due to the body's angular velocity. Just writing it all as before. And since we know the acceleration of point B, we just solved for it, Now, notice we don't know the angular acceleration of BD, the vertical bar, the connecting link. But we do know the angular speed of BD. That was solved before. Notice we can't get to acceleration before we've got angular velocities. So the only thing that's really unknown in the equation so far is the angular velocity of BD. Now notice this is still written out as a vector equation, so technically we have two equations here, not just one. We have an x component and a y component. Now notice we haven't solved it yet, right? Let me go back and point out we haven't solved for the angular acceleration of point DE. We have to bring in the information that point D is constrained to move in a circle about E. So how do we do that? Well, we analyze bar DE. In other words, we write another relative acceleration equation. So the acceleration of point D, what they're doing here is they're just saying, okay, D, I wish they'd written the whole thing out. They didn't. They're actually analyzing it with respect to E. They just unfortunately did not write out the full equation. The full equation would be that the acceleration of point D equals the acceleration of point E plus the relative acceleration of D with respect to E. What they've done is they've said, well, the acceleration of point E is 0, so we're not even going to bother putting that in. And the relative acceleration of D with respect to E is going to consist of a tangential and normal piece. So that the tangential piece is the alpha dE, the angular acceleration of body dE, crossed with the vector from E to D. And you know they're taking E as the reference point because it's the second point in the position vector. It's point E. And then they write the normal piece as, again, a negative omega squared, the angular velocity of bar dE, times the vector r from E to D. And notice again they've taken it in the negative direction. All they really mean by that is that the normal acceleration points against vector rd with respect to E. And so then they just expand the terms out. So they're taking the actual cross product, which you often have to do. So you have to be able to write vector RDE in vector format. And using the position information, which is known, right, vector RD with respect to E has a negative 11I component and a positive 3J component. Using that position information, remember I said the position information has to already be solved for. That's why, because we need the vector here, that position vector. They can write everything out. Notice the angular velocity is already solved for, so they can plug that in, and they're just writing RD with respect to E, again, the relative position between D and E. And then just go, pardon me, and then just going through the cross product and adding the various components together to get the horizontal piece by itself, the I piece by itself, and the J piece by itself. Now, you may be a little bit rusty on cross products. When you take K cross that, so look at the second line where it's alpha dE, K crossed with the position vector RD with respect to E. When you take that cross product, you have to take K cross I and K cross J to figure out where these things go. So K cross I, the way to think about that, K, think about an X to the right, Y up, and Z out of the board. Taking K, which is out of the board, crossed with I, well, you point your hand in the direction of K, which is out of the board, and then rotate your fingers that are pointing in the K direction through the smallest angle to get to I, and then whatever direction your thumb points, that's the resulting cross product. Well, that's a positive J. So on the next line, they write negative 11 alpha dE J. I thought it was positive J. Where'd that negative come from? Well, the negative just wrote along from the negative 11 in the scalar piece of the vector RDE in the I direction. So that's where that first term comes from, negative 11 alpha dE J. And then K cross J, well, again, point your fingers out of the board, rotate them into the J direction, which is up. That's a negative I direction. So you notice the next term in the third line says negative 3. Well, where'd the 3 come from? Well, it came from 3J in the position vector. Alpha dE, that makes sense. That's the multiplier on the K. But where'd the negative sign come from? Well, remember, we took the cross product of K with J and got negative I. So that negative now has come from the cross product. And then finally, after that, they've got plus 71.27. Where did all this come from? Well, we're actually done with all the cross products. We're done with that first tangential acceleration piece. Now we're working on the normal piece that involves the omega squared. So this comes from 2.5455 squared times 11, and it's negative times a negative, so it's a positive 71.275. And then negative of 2.54, etc., squared multiplied by positive 3 gives us a result that is a negative 19.439. And notice the normal piece is easy because you don't have to worry about the cross product. You're left with the same unit vector as you started with. With the tangential piece, you end up having to calculate the cross product and figure out the correct directions, whether they're positive or negative, for the unit vectors. So then just collect all the I terms together, collect all the j terms together, and now you have an expression for the acceleration point d. Notice this is a independent expression for the acceleration of point d. Now what we can do from the previous page is bring in the other acceleration expression we have, equate the I components together of those two vectors. So the I components, let's see. Oh, I see. They've equated the j components first. So 7.29 or 7.289 equals the complicated j. It's not really complex, but the j component from the equation that we've derived for link DE on this page, and then equating the I components of those two vectors, and then you just have two equations to solve for the unknown. Now, it looks like we've got two equations to unknown, so we can solve for the angular accelerations. So that's how this works. You always break down the acceleration into a normal and tangential piece. Sometimes you got a cross product. Well, in fact, almost all the time you have a cross product along the way to consider. But then you equate components, realizing that your vector equations are actually two equations in one, and then you've got it. All right. So finally, if the clockwise angular velocity of crankshaft AB is constant, so it's rotating clockwise, which of the following statements is true? Is the angular velocity of BD constant? That's the connecting rod? No, there's no way. It's going to vary, right, as it moves around. The linear acceleration of point B is 0. Linear acceleration, no, that doesn't make sense because B has a normal acceleration. The angular velocity of BD is clockwise. Counterclockwise. Actually, that does make sense. If the crankshaft is rotating clockwise, then BD, the connecting rod, has to rotate counterclockwise. So I'd say C. The linear acceleration of point B is tangent to the path. No, the linear acceleration of point B is pointed from B to A. It's not tangent to the path that B is moving on. So C would be the correct answer.